Here's my thoughts on how to build an infinitely tall tower. The problem with building a really high tower is the material at the bottom could eventually get crushed. So I figured this is one way you could build a tower where you don't crush your base, and theoretically you could go to infinity. What made me think of this was from watching the movie World War Z, where all of those zombies were forming a huge zombie pyramid to climb that big wall. At first I figured there's no way that humans or zombies could form such a huge pyramid because the ones at the bottom would be crushed. Then I thought maybe all those zombies on top are just climbing over a bunch of busted up zombie bodies underneath them. Then I started thinking about which bones would be broken first for those zombies at the bottom of the pyramid. Would it be their vertebra? Would they get these vertebral compression fractures? Or I thought maybe the neck of the femurs or the hip bones, those might break. They're kind of smaller. Maybe the tibia and fibula, I don't know. But then I started wondering if there would be a way to mathematically construct a tower that could be theoretically infinitely tall and the members at the bottom wouldn't be crushed. And then I started thinking about how cheerleaders build their pyramids. Typically, if you're looking at like high school cheerleaders or something with just females, there'll be two females on the bottom as the base, and each of them will hold up a foot of the person on top of them. So then that way each member at the bottom only has to support half the weight. But then I wondered if you could just take that idea on out to infinity. So this is what I got. We'll have a person here or a pillar, whatever, at the top. I'll call that member C. Then that'll go down to member B, and then B will go down to members A. And just for simplicity, let's say the masses of all the members are identical. So the mass of A equals the mass of B equals the mass of C, and so on. As you can see, B will support half the weight of C. And then A, if all of these are A, so this would be A would support half the weight of B and half of whatever B is supporting. So it'll look like this. B sub S is what B supports. B will support 1/2 of C. And then if you look at what A supports half of something. So let's just put A sub S equals 1/2 of something. So that 1/2 will be the weight of B plus whatever B supports. But then if you notice what B supports here, B sub S is 1/2 of C. So that means we can change B sub S into 1/2 of C, and it'll look like this. A will support 1/2 of the quantity, B plus 1/2 of C. Distribute your 1/2 through, you get 1/2 B plus 1/4 C, and on and on and on. Or as they said on Seinfeld, yada, yada, yada. So it could actually end up looking like this if you have several levels. A sub S on what A supports will be 1/2 of B plus 1/4 of C plus 1/8 of D, and on and on. You just keep doubling your denominator. With our plus signs here, that'll be summary notation. So we can take the summary notation of n equals 0 of 1 over 2 to the nth power from 0 to infinity. That will be 2 to the 0 power will be 1. So 1 over 1 equals 1. So it'll be 1 plus 1/2 plus 1/4 plus 1/8, and yada, 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 as they said on Seinfeld. This will approach to, you could say, the limit of the sum from n equals 0 to infinity of 1 over 2 to the nth. That limit will approach 2. And basically it would look like this. A has to support its own weight on the bottom plus half of B and everything above that. The interesting thing about this fraction here, it comes out to be equal 2. And so you'll have a full circle here for your own weight because A has to support its own weight. Plus, we just start dividing this up into fractions here. We will have 1/2, then we'll have plus 1/4, plus 1/8. And notice as you keep cutting this pie chart into smaller and smaller slices, you'll eventually approach 1 on this pie chart. So in other words, you'll never go over 2. So that means A will never have to support more than twice its own weight, no matter how high that tower goes, even if it goes to infinity. If you're looking at how much mass A has to support, you don't have to include A itself if you don't want to. In that case, you can just ignore this whole pie right here, and we'll just look at this pie right here on the right. So no matter how many slices you cut that pie up into, when you add all those pieces together, it'll still come out to be 1. This means that member A will never have to support more than its own weight over its own head. And how you change the formula to represent this is instead of having n start at 0, you just have n start at 1. So you end up with just 1/2 plus 1/4 plus 1/8, and you won't have that 1 right there at the beginning. When you draw this out diagrammatically here, you'll start getting these really long horizontal members, which in reality would start causing some bending because no bridge can be infinitely long. But I figure you could do a 3D interwoven or intermeshed structure. I think of like Tinker Toys that kids play with. Since these vertical members here are so small, you can start intermeshing these with each other and have them go at all different orientations. So you could have some horizontal here on the paper, some going into the paper, and they can simply all be overlapping with each other. So you won't end up with these really long horizontal members. The catch on this though is when you get up to say 10 levels, that'll be 2 to the 10th power. So that means on your bottom here, you'll have over 1,000 members just to make this 10 levels high. So granted, this might be more of an exercise in logic instead of one in practicality, but I figure it's nice to know that at least theoretically there is a way to make a tower very tall. And next page. Here's some problems I came across if you put the levels in an additive pattern instead of a multiplicative pattern. And by the way, as I often say, none of this is my field. These are just things I came across on my math doodles when I was just playing around. So I imagine that structural engineers will have their own terminology for all of this stuff I'm going to show. So at any rate, levels must be multiplicative, not additive. In other words, they need to go by multiples, 1, 2, 4, 8, for example, not 1, 2, 3, 4, where they're added. You could do 1, 3, 9, 27. But if you're going to put them in groups of 3, then they would need to be in a 3-dimensional tripod shape and not linear. And actually, I'll just go ahead and draw a picture here to show what I'm talking about here. You have 3 members here, and then those 3 will go to 1 right here, and then below this will go 9. So you'll have like this. It'll go 9, 3, 1, multiples of 3. These should not be 2-dimensional from what I can figure because all materials will naturally have some flexing. And so that means that the middle members will end up getting more stress than the outer members. But if you put them in a 3-dimensional tripod shape, then that means that all the members could have equal stresses. So here's kind of what I'm talking about right here. I'm going to go ahead and move this up right there. Here I'm going to do additive. So let's say there's 20 newtons of force, 20,000 newtons of force, whatever, pushing down on this one, or that's this mass, or this force pushing down. Then that means this has to be divided up into 2, so 10 and 10. This 10 has to be divided up into 2, so it'll be 5 and 5. 5 will go on this pillar, 5 on this section right here. Same thing on this side, 5 here, 5 here. We got 5, 10, 15, 20. It all adds up to 20. But this middle column right here will get more force on it because it gets the force from this side and this side. And this is kind of what I was illustrating right here. If you had, if you went up in multiples of 3, but if you did like a 3-dimensional tripod shape, or like a, you know, like a stool with 3 legs, and you push in the middle of that stool, then all 3 legs will have equal force. I put this gap here to show that all materials are naturally going to flex. And theoretically, if this was totally rigid, so if we were dealing with a toy block, for example, that had no measurable flexibility, and you were to push down with a unit of 10 here and 10 here, then that would be 20, and that 20 would be divided up evenly between all 3 of these bottom pillars here. But when we're dealing with macroscopic level buildings and towers and such, I think there's going to naturally be flexion, which means these 2 ends right here can independently push down on this and create more force right here on the middle column compared to the outer columns. This means we will not have equal weight distribution, and the middle columns will be crushed before the outer columns. I figure this is a materials cost issue, so you need to know how much cost or material you'll need for each column. But with this model, you're going to have different columns under different amounts of forces, so it might make it a little harder to predict. I was just thinking how there appears to be an analogy with electrical current. If you change your force into current, then you can imagine a current flowing through all of these members here, and you want that current to flow evenly. But when you're dealing with large macroscopic buildings or towers, you're going to have some flexion naturally. So that could create somewhat of a short or a path of least resistance for that current or force to flow down through this middle column more than the outer columns. If you build your tower here multiplicatively, say in groups of 2, This top one right here will have a force of 8. That gets divided up into 2, so it'll be 4. Then that gets divided, and that'll be 2, and that'll be 1. And it looks like you could easily prove that the weight will be, or the force will be distributed evenly because this member is identical to that member. They both have to support half. This whole structure is identical to that structure right there, thus showing the innermost members will have identical force to the outermost members, so same force. This just makes it nice and predictable, so you know how much material you're going to need for each column or each vertical member. And on this last diagram here, I think this shows another problem with doing additive levels instead of multiplicative levels. If you have a block right here on top, you could just do this with Jenga blocks to find out what will happen. This block on top will push down on the 2 blocks below it, but it only pushes on the middle halves of each of those blocks. And if you're having a force push down in the middle on this lower block here and on the end of this block, then the average location of that force will be halfway between those 2 points, so it'll be at the 1/4 mark right there on the inside of that block. And same on the other side. Thus we have more force pushing down in the middle than on the ends, and that force will be conducted on down to the middle block right here. So if you want to build a little wall here with just some Jenga blocks, for example, you'll find out there's more force on this middle block than the outer blocks here. You can just lightly tap those outer blocks and they'll slide out because most of the force will be on this middle block. I think this might be the best illustration of why the levels need to be multiplicative and not additive. What I did here is drew a dashed line cutting off this section of the pyramid right here, so we can just ignore everything to the right of that. And if we just look at these members right here on the left, we start out, we have 1 member on the top being supported by 2 on the bottom, so it's 1/2 or 1/2. We take it down to the next level here. We will have 3 members on top, 1, 2, 3, being supported by 3 on the bottom, so it becomes 3/3 or 1. And then it becomes 6 force, 1, 2, 3, 4, 5, 6. 6 members on top being supported by 4 on the bottom, or 1 1/2. So the trend appears to go, it increases by 1/2 for every level that you add. As this fraction gets larger, it shows that the bottom members have to support more and more weight, and thus they'll eventually be crushed. That is, if you keep adding levels. I wasn't able to prove that this will continue to increase by 1/2 for every level added, so I don't know what that formula would be, so I'll have to save that one for the mathematicians. But I do have a way to show that this fraction will continue to increase forever. If we just look at the members to the left of this dashed line here, and say we have 2 members on the bottom supporting 1 on the top. So now instead of having a pyramid that's 2 members high, we want to go to 3 members high. That means we're going to add 1 on the bottom, and we're going to add 2 more on the top that has to be supported. And then if we want to add another level, then what we're going to have to do is take our 3 members here on the bottom, 1, 2, 3, that's supporting 3 on top. We'll have to add another member right here, and this 1 member gets added to the bottom, that's the base, but then 3 members get added up high that have to be supported. So as you continue to add levels going down this pyramid, the denominator will only increase by 1, but the numerator will increase by however many levels you have above that bottom level. I just use summary notation right here, or if we put the number of levels in the denominators, which means if we're down to 5 levels, we'll have 5 members, or 5 in the denominator. And then the top will be the summary notation, starting with 1. It'll go 1 plus 2 plus 3 plus 4, so it'll be 5 minus 1. So we'll have summary notation of n equals 1, starting with 1, and going up to the number of levels minus 1. This will equal the amount of weight that has to be supported by each bottom member or each bottom column. So, for example, if we just have, I'll move this up right here, level 5, so we'll have 5 levels, put 5 in the denominator, and for the numerator, we'll have 1 plus 2 plus 3 plus 4, which will be 10/5 or 2, which is what I have over there. I suppose the summary notation really isn't necessary to see that as you keep increasing levels, then there'll be more force per member on the bottom members. And again, showing that the levels need to be multiplicative and not additive.